Great. Perfect. So great. So it's a great pleasure to kick off this seminar. We'll see where it's going. I hope it would be success and you guys all like it. So for this special beginning, we have also a very special guest. So it's my great pleasure to have here today Michael Krivelevich, with whom we're going back long time, working together and doing various things. So it's a great pleasure to have him here. I will not go describing all Michael's achievements. For that, I included a short bio, which you could have read on the abstract. The title of the talk is Improving Graphs Parameters Through Random Perturbation. Please, Michael.
Okay, thank you, Barry. It's you can hear me, correct?
Yes.
Okay, it's a great pleasure to be here, and thank you for this nice introduction. Our cooperation with you really goes way back, and it might be the case that we started cooperating before some attendees of this seminars were even born, but let's not go into it. Okay, so I'll be talking about improving graphs parameters through random perturbation, and of course I will aim to explain you what's the meaning of these terms here, what's graph parameters, which parameters I have in mind, what's random permutation, and what exactly we are striving to improve. So this is a joint work with Elad Aigner for F and Dan Hefetz. Both of them are from the University of Ariel. And I think both of them are depicted here in some kind of official corridor for pictures. So you can obviously say that they both have very strong background. Okay, so what I'm talking about. The setting, or rather meta setting, will be as follows. So suppose we have a graph on n vertices, and in addition, we impose some assumptions on the graph. So two basic assumptions are as follows. Either we will assume that its minimal degree is at least k, or we assume that its independence number is at most c, or maybe both, or you can think about some other assumptions to assume. And then the question, or rather meta question, would be as follows. What can be said about various graph-theoretic parameters of G, given A1 or A2, or both of them? And we will see fairly shortly that actually you cannot say that much, and there is some room for improvement, and the improvement will be achieved through randomness. So the parameters I'll be talking about are as follows. So they are pretty standard. We will talk about connectivity, or rather connectivity. We will talk about diameter. We will talk about large complete minors, and we will talk about large complete topological minors. But in principle, you can take your favorite graph theoretic parameters and try to see what can be said assuming A1 and A2, which is really a very classical extremal graph theoretic setting, or what can be said if on top of it you impose some randomness. Okay. So let me brief for you basic definitions, which are fairly standard. Connectivity, or rather k connectivity, as usually we say that the graph G is k connected, k vertex connected, if you cannot destroy connectivity by deleting k minus 1 or less vertices. And kappa of G is, as usually, stands for the maximal value of k, such as G is k connected, which is the vertex connectivity of G. Second parameter is diameter. So diameter is defined as usually as the maximal distance between the vertices of the graph. And if your graph is disconnected, namely if there is a pair of vertices which are not connected by any path, then the distance between them is not well defined. In this case, we put diameter to be equal to infinity. So here's the third parameter, or the third notion, is that of complete minors. Here I'll be talking about complete minors. So let me define it for you. Let me remind you the definition of it. So we say that KK, a complete graph on K vertices, is a minor of G, and we denote it by this KK some curly a less than G. If the following holds, you can find K disjoint subsets V1 up to the K in V of G, such that each of them spans a connected graph. And moreover, there is an H of G between every pair Vi and Vj, I different from J between 1 and K. So if that's the case, then you can go back to the more usual or standard notion of contraction in minors. You can contract each of the pieces Vi into a single point. And what you get after contraction is exactly a copy of KK, and hence what you have here is a minor of KK. So here's a picture. If you look at this picture, the four shaded areas form a connected piece in the graph, and you can see that there is an edge between each pair of shaded pieces, and therefore what this picture gives you is a minor of K4 this form. And we want to measure it quantitatively, and therefore we define the parameters contraction clique number of G, CCL of G to be the maximal value of K such that KK is the minor of G, which is in words the size of a largest complete minor in G. So a related notion, a fairly close one but still different one, is that of topological minors. So let's talk about complete topological minors. So we say that a KK is a topological minor of G if the following holds. You can find K disjoint vertices V1 up to Vk, such that for every parameter Vi and Vj, we can find a path Pij, and those passes are internally disjoint. Namely, what we get actually is a subdivision of Kk. So a subdivision of a graph is obtained by taking the edges of a graph and inserting any number of vertices, of intermediate vertices into every edge, and the number can be different for different edges. So the subdivision topological minor is the same thing. So let me give you a small animation how you get a subdivision of K33 in the Peterson graph. So you start with Peterson graph. Now you delete the first vertex. Then you contract or swallow vertex, yet another vertex, yet another vertex. Altogether, you are left with these 6 vertices, and you see this by definition of using this action of suppressing the vertex or deleting the vertex. What we get eventually is a subdivision of K33 in the Peterson graph, which actually shows you, in particular, due to Karatovsky's theorem, that Peterson graph is not planar. So we want to measure it quantitatively, so we define the notion of topological clique in G. So TCL of G is a maximal value of K, such that KK is a topological minor of G. So you can compare these two notions, and you can see easily that if you have a topological minor of KK, you have a minor of KK as well, meaning minors is more in comprising notion than notion of topological minors, and therefore for every graph G, CCL of G is at least as large as TCL of G, but actually the difference can be quite substantial, and we'll see some concrete examples soon. So that's the graph properties we are trying to, or graph parameters we are trying to look at, and we will see what can be said just by imposing A1 or N2, and what can be said by imposing A1 or N2, and by adding some little randomness. Okay, so let's look, first of all, let's compare between the assumptions. The first one was assuming something about minimal degree, and the second one is assuming something about independence number bounding it from above. And we would like to say that A2 is essentially stronger, even much stronger than A1. So let's argue briefly why. By Turin's theorem, we know that the independence number is bounded from below by n divided by the maximum degree of G plus 1. Or even n divided by the average degree of G plus 1, which means that if you have an independence number bounded from above, you know that the average degree of a graph is large. If the independence number is at most t, then the average degree of a graph is at most roughly n divided by t. By not only this, since the notion of having independence number bounded is hereditary, namely, if you take any induced graph G naught of G, you still have the same bound on the independence number, you can argue quite easily that every subset of linear size has most vertices of degree in its spanning subgraph has most vertices of degree at least of order n with c. So in particular, you can find a subset of linear size with minimal degree of order n with c. So this means that if you assume independence number bounded from above, by this assumption, you can have an easy global reduction to a graph whose minimal degrees of order n over t. So in some sense, A2 is stronger, at least feels stronger than A1 globally, and we will see some manifestations of it. There will be some results which are valid assuming A2, but are pretty much invalid assuming A1 only. Okay, now let's look at some examples to see how far can we get just by assuming A1 and A2. And the examples are really very standard prosaic. The first one is a collection of disjoint cliques. So we have a graph which is composed of n over k plus 1 cliques of size k plus 1. Let's assume divisibility. So in this graph, minimal degree is k. Actually, you get exactly k regular graph. And the independence number is exactly n divided by k plus 1. But this graph is disconnected. We cannot talk about connectivity. And so in particular, its diameter is infinite. If you want to get a similar picture, but which will be so okay. Before going to a similar picture, so here for trivial reasons, the clique contraction number and a topological contraction number is are both of value k plus 1. Okay, so here's some short variant of it. So you have, if instead of cliques we take disjoint random graphs, suppose we have a collection of n over k random graphs. Each of them is distributed according to a k n 1/2. And let's assume, to make life simple, that k is much larger than log n. So what do we get here? So here with high probability, I will use this notion from now on, and I will abbreviate it by WHP. So here with high probability, we have minimal degree k over 3. We are, of course, disconnected because these graphs are vertices disjoint, and therefore diameter is infinity. As far as the complete minor goes, you can get here a complete minor of size order k divided by square root of k, which means we are losing a square root of k factor compared to the previous example. And as for the topological minor, the difference is even sharper here. We will get a topological minor of order only square root k. This is a classical result of Erdos and Krivelevich, which could be used, and I think it was used to disprove the quite famous and challenging up to that point conjecture of Hayek about connection between coloring and topological minors. And in retrospect, that's a fairly straightforward volume argument. Okay, the third class of examples is of complete unbalanced bipartite graphs. So it's depicted here. Think about k being much smaller than n. K is some power of n, say, which is less than 1. So what do we get here? So here we get a complete minor of size k plus 1. And this is because in your minor, every branch set, but at most one, should contain a vertex from the smaller part, because otherwise you are just disjoint. And therefore, a trivial bound, trivial upper bound on the clique contraction number is k plus 1, and you get a similar bound on the topological clique number. So if you summarize over all these three examples, you can see that you cannot get very far just by assuming A1 and A2. You can't really say anything about the diameter, about the connectivity. You can say some things about a topological clique or minor, or clique minor, but up to some limited extent, which means it won't take you very far, which sounds a bit sad. But you know, as frequently in life, what's sad for some people is a source of happiness for some others, or inspiration. And indeed, in some sense, this somewhat a limited advantage we can get from A1 and 2 can serve as a motivation to improve it by using some randomness. And that's our way to proceed. We will use little randomness, and we will see that with little randomness, we can do really big things. So a possible remedy, in a way, in retrospect, it is quite natural, is to add random edges on top of your graph G. So what you get is the so-called model of randomly perturbed graphs. I will comment on this notion in minutes. So formally it's defined as follows. We start with a graph on n vertices, any graph on n vertices, and typically we assume that your graph belongs to some particular class. It has some structure, for example, it has A1 or A2, or both of them, or some other property. And as we've seen in previous examples, the properties we impose by themselves are not enough to deliver what you aim to deliver. And therefore, what you do is you put a random part on top of it. So you take a random graph R, distributed according to G and P. So P is typically a function of n, and hopefully it's actually a fairly small function of n, meaning you will add a really small quantity of random edges. So to remind you, G and P is a very standard definition. As a vertex set is 1 up to n, and for every pair ij is an h of G in with probability P. P typically is a function of n, typically a Venetian function of n, and you do it independently for different edges. Namely, you have n choose 2 coins, which are identically distributed by independent, and they might be biased, and typically they are biased. You flip these coins for every pair of edges, and based on the result on this coin flipping, you decide whether you put an edge inside or not. Okay, and then you have your graph G. You impose on top of it your randomness R. So altogether we got graph H, and the question is, what are the typical properties of H? We are talking here about typical properties because a random component is involved here. Okay. A small comment about perturbation. So typically perturbation means some non-edges will go into edges and some edges might go into non-edges. So if you really want to be really formal, perhaps you should, instead of taking the union of G and R, you should take a symmetric difference between G and R. But in most of the cases, more or less in any imaginable case, deleting edges first doesn't make much difference. You more or less get the same graph. Minimal degree more or less stays the same minimal degree, and therefore deletion is inconsequential, and hence instead of talking about deletion and addition, you typically add few random edges on top of your graph. Okay, so let me cover some history. So probably the motivation, at least in retrospect, goes to these two smiling gentlemen, which are Spielman and Tank, who introduced a quite famous and extremely influential notion of smooth analysis in the analysis of algorithms. And what they proved informally is the following statement. For any continuous linear optimization problem, so you have a linear cost function and you optimize over the domain formed by linear inequalities. So for every linear optimization problem, you start with your problem, but then you shake or perturb it a bit, slightly, according to some well-defined law of distribution, because your problem is actually a collection of, it's a cost function and constraints. Each of them is a collection of numbers. So you perturb these numbers ever so slightly, and you get a random instance. And it turns out, and that's what you need to prove, that you typically get an instance which is polynomially solvable by the simplex algorithm in some particular version. That's really a very striking result, because a simplex algorithm theoretically more or less for any imaginable pivot rule is not, pivot rule is a rule which says you are at a given vertex which edge to take, which improves the value of the cost function. So more or less for any pivot rule, there's an negative example showing that this pivot rule in the worst case performs super polynomially in the size of the problem. And yet for problems which are taken from practice, simplex algorithm is known to be amazingly efficient. So a possible explanation is that if you take a problem from real life, you obtain it by measurements. Your measurements are not exactly precise, which means there's some element of slight random noise in your measurements. So basically, the real problem you're trying to solve after measurement is actually a slightly perturbed version of the problem, and hence you can hope to have it solved efficiently by the simplex algorithm. So this was a very influential paper which made a lot of noise and attracted a lot of accolades. So it was awarded Godel Prize in 2008. It won one of three, I think, items cited in Dan Spielman citation for Niemann Prize. So that's really very, very influential. So back to combinatorial world, or back to graph-theoretic world, probably the origin of the whole business is in the paper of Bowman, Fries, and Martin from 2003. I think it did not predate the paper of Spielman and Tank, and I'm not sure the authors of this paper were aware of the work of Spielman and Tank, but in retrospect, it's only logical to connect these things. So they wrote the following paper, and the title of the paper is very, very descriptive. The title is How Many Random Edges Make a Dense Graph Hamiltonian? So you can imagine what the scenario is. So here are these three fine gentlemen. And the goal would be to start with a graph which is assumed to be dense and to put some random noise R on top of it, and eventually to get with high probability a Hamiltonian graph, namely a graph containing a Hamilton cycle. Okay, so they prove the following theorem. So we start with a graph of n vertices, and the thing we assume is that its minimum degree is at least C1n for any constant C1. So this assumption is nice. It assures you that your graph is what's usually called locally dense. All degrees are linear, and this assumption by itself is not enough to take it to Hamiltonicity. Think about, for example, a complete bipartite graph with uneven sides, which is not Hamiltonian, and all degrees are still linear in it. And then you do the following. You take your edge probability P to be C2 over n. So C2 is a function of C1, but for as long as C1 is a constant, C2 is a constant as well, which means you add typically linear number of random edges. You start with a graph with quadratically many edges. You add on top of it a linear number of random edges, and you look at the perturbed graph, union of G and R, and what they were able to prove that after this random addition, you get a Hamiltonian graph, namely containing a Hamilton segment. So you can ask yourself whether you need so many random edges. Maybe you can get away with even less random edges, less than linear. That's not the case. For example, if you take a graph G to be an unbalanced complete bipartite graph with parts of size C1n and n minus C1n, then deterministically for this graph, you need to add linearly many edges to the larger part to make it Hamiltonian, which means you do need a random noise of amplitude linear and random edges. But one thing to notice is that in this previous example, you can observe that you have a huge independence number, and perhaps assuming something about independence number as well can make your life much easier. So maybe if in addition to imposing an assumption about the minimal degree, which is A1 in our terms, you impose an assumption about independence number, which is A2 in our terms. So perhaps you can get away with much less edges. And that's indeed the case. And that's the second theorem, which I reformulate here and state in some particular case, it goes like this. So we have a graph on n vertices, any graph on n vertices with minimal degree C1n. And on top of it, we put a very, very mild assumption in the independence number. We assume that the independence number is at most C2n for some C2, which is a constant for as long as C1 is a constant. Okay. So this is a really mild assumption. So typically for a graph with linear degrees, its independence number should be only logarithmic. So here we allow to have really huge independence number, and yet it turns out that this allows to make a huge progress. If that's the case, then imposing a random noise of really small amplitude. So the H probability P is taken just to be above 1 squared. Namely, you can take any quantity of random edges tending to infinity, and then the union of G and R is typically a Hamiltonian graph. So you see that if you assume an assumption about minimal degree, and the assumption about alpha of G, so you can improve it even more, and you can, by using really very, very little randomness, you can get a Hamiltonian set. So the conclusion is the moral of this story, and that sounds very encouraging, that adding little randomness can help improve the situation big time, or at least you can hope to do it. So this is very nice, it's very encouraging, very inspiring, and indeed this has become a very popular subject, so you can be happy about it. And since then, several dozens of papers have been written about this subject. So that's really a nice subject, and that's actually also a good model for producing new questions. You take your favorite graph properties, property, minimal degree or independence number or something else, or minimal degree can be assumed to be not just linear and by any function of n. You impose some random noise on top of it, and you ask what's the amplitude of random noise required to get typically your property. That's a nice subject. Very good. Now let me describe our results. So the first target says there will be 4 of them, and each one of them corresponds to a different target or different type of the graph property we are trying to get. So the first one is to get our graph after random permutation, to have it highly connected. So the target is to have S connectivity. S can be a function of K. Okay, so here's the theorem. We take a graph, any graph n vertices. We assume its minimal degree is at least K, and for technical reasons, we assume K is little of n, K is sublinear n, because the case of K linear n is A easier and B has been covered before. So that's assumption A1. And now on top of it, you impose random noise, but let's beforehand set our goal. So we are shooting for S connectivity, and S in our goal can be as high as linear in n. It's really unrealistic to take S beyond K, because if you want to have eventually connectivity beyond K, this means you need to touch each and every edge and touch massively, which means lots and lots of edges. But you can get as far or as high as linear in K. Okay, So you impose a random noise R is GNP, and P is of order S plus log n over K divided by NK. Namely, you add typically S plus log n K times n over K random edges. So if S is small, the prevalent expression is log n over K times n over K. If S is large, then S n over K is the expression we are getting here. Okay? And then after this addition of random edges, which is still fairly few, you get a graph which is S connected. So you can start with any graph. You assume just a minimal degrees. Your graph can be even disconnected. And you, after this addition of relatively few random edges, you can get high connectivity. You can ask yourself how optimal this is, and this is fairly optimal. And this is fairly optimal because of this standard example. If G is taken to begin with to be a collection of cliques of size K plus 1, then this graph of minimal degree K, actually K regular graph. And if you want to get your eventual graph as connected, you need at least S edges touching every clique, which means you need to add at least orders S n over K random edges. And this justifies this S here, S n over K. And also I need to touch every clique, and this requires of you adding at least n over K times log of n over K edges. That's the usual addition of log to for coupon collector. So this shows that our result is basically optimal. Result number 2 is about small diameter. So we start with the graph with a large minimum degree and vertices. Minimum degree is K. K is again assumed to be function of A for K, which is linear, and the much more delicate results available, and it's in some sense easier. And you put random noise on top of it, and the magnitude of random noise is really fairly small. So you just assume that your H probability P is larger, much larger than log n over K divided by NK. You basically add fairly close to n over K random edges, really negligible amount of random noise compared to the size of the whole graph. So in order to introduce the result, let me define quantity Q. Q is defined to be 1 minus P to the power K squared, and behaves asymptotically like P K squared. Then with high probability, the diameter of the resulting graph G union R is of order log of n divided by K divided by log of NQ divided by 2K. So if you want to decipher this result, you can notice in particular the following things. For example, if your quantity K and P is of order polynomial in n over K, is at least as large as n over K to the epsilon, then what you get here, that's an easy calculation, what we get here is a graph of constant diameter. So the constant depends on epsilon, but still after adding relatively few random edges, you get a graph which has constant diameter, which means you can easily hop from vertex to vertex in a constant number of steps. That's a huge improvement. Okay? And the optimality is more or less the same. You can take the same example as before. If you start with a collection of disjoint cliques, you start with a graph which is not even connected to begin with, and you do need some randomness to it. And adding randomness of this magnitude is more or less not only sufficient, but is also necessary. So the third result is about large complete minors. Our goal will be to start with the graph having property A1, or actually here we assume A2 rather than A1. I explained why. And we want to add some small random noise on top of it. And the goal is to get typically a large complete minor. Okay. So here's a theorem. So we have a graph GVE. We assume that the vertex set is 1 up to n, just to superpose it with a random graph GNP. And we assume here now that alpha G is at most C, namely instead of A1 as before, we assume A2, which is a stronger assumption. And I will explain you why we need to assume A2 and not A1. So we put on top of it a random graph R distributed according to GNP, and the assumption on P is fairly modest. You just need to put linearly many random edges. So P is C of n, and C can be even a small constant. You don't need your graph to go beyond phase transition, just taking 0.01 divided by n for the value of P would suffice here. Okay. Then with high probability you get a minor of a graph of average degree n divided by square root C. So why do we talk here about a minor of average degree? That's a fairly standard way to get a complete minor, because from this using a standard result, very classical result. By Kostechka and Thomason, you go from a minor of a graph of large average degree to a complete minor, and you only lose square root and factor. So altogether, we get here after this random addition a complete minor. We get typically a complete minor of order n divided by square root c times square root log n. Okay, so let's discuss two things: optimality and why A2 and not A1. So first of all, about optimality. If we start with a collection of cliques of size k, n over k cliques of size k, then here the independence number is n over k. We have here roughly k n over 2 edges. So let's think about getting a large minor. The point is that if you have a large complete minor in your graph, if you have a complete minor of size t in graph H, then you better have t2 edges in your graph H, because you need to connect between every two branch sets, and there are t of them. Which means that for any graph H obtained randomly or not, its contraction clique number is of order at most O of a square root of edges. And therefore, if you look at your random graph, if you random addition G, the union of G and R, then deterministically its clique contraction number is of order at most square root of E of G of E of R. Of course, you assume that your random noise has smaller magnitudes on your base graph, which means you typically stay with the same order of magnitude edges, which is Kn. And therefore, the best you can hope for is to get a square root of Kn edges. And square root of Kn is exactly n divided by alpha of G, which means after this small square root log n correction, you get the optimal thing in this argument. Now, why do we assume A2 and not A1? So here's the explanation. So if you take a complete bipartite graph with parts k and n minus k, part A has size k, part B has size n minus k, and think about k being much smaller than n, but let's say larger than square root n. So what do we get here? So here we can argue deterministically that the clique contraction number of G and R is at most k plus what you get inside part B. Because out of your branch sets, only k touch the smaller part A, and therefore the rest should come from B. And therefore, you basically are facing the question, okay, you put your random graph inside linear large set. What's the complete minor you can expect? And it's quite easy to see by H count that the best you can hope is to get a square root n in order of magnitude. And therefore, altogether, you get square root n. Okay? So which shows that if we impose here just minimal degree, so instead of getting something much better, you get only square root. Okay, you get here much smaller than you would get by assuming A2. So A2 here is much stronger than A1, and it helps. Okay, so the first result is about a large complete.
Michael, I have a question here. Right? So when you're applying Kostechka-Thomason, you will lose an additional log, right? Square root log.
Correct.
But potentially it's possible that maybe because of the structure of randomness, you don't have to lose it. Do you know anything?
This could be benefit. This we didn't know to prove, but even for a random graph, as you should remember, because of our paper, going from a square root and divided by square root log n to square root and takes some effort. So that's the result of Kondondostos. So this certainly might be true. So the result is tight. If you want to get a graph of a minor of a graph of large average degree, then we get the best. If you want to get a complete minor, we are losing by Kostechka-Thomason this square root log n factor. It could be that you can improve, but that's certainly not trivial. But that's a nice question. Thank you. Okay. Okay. So the next goal and the last goal is to get a large complete topological minor. So here we start with a graph of n vertices. Its minimal degree is k. And we assume technically, because k is actually going to be our asymptotic parameters, that k is much larger than 1, namely k tends to infinity as n tends to infinity, but that's really a very mild assumption. So we assume A1 here. And then on top of it, you impose your random noise. And the random noise is G and P is taken to be C over n. So here, technically, we need our P to be of order inverse linear n, with sufficiently large absolute constant. Sufficiently large is kind of not exactly descriptive term here because sufficiently large here probably something like 100 would be easily enough, maybe even 10. So that's not the astronomical constants from the regularity lemma. I'm not hiding anything scary here. That's really fairly small constant. And then you unite G and R, and what you can prove is that with high probability, the topological clique number of G union R is of order at least minimum of k and square root of n divided by log n. So let's try to understand how good is this result. Let's talk about optimality. So first of all, for any graph deterministically and trivially, the topological clique number of h is most delta of h plus 1 because if you have a minor, a topological minor of kt, for every branch versus of a minor, you need to have t minus 1 passes leaving it. And therefore, there is a very rigid and very simple upper bound on the topological clique number. And hence, if you take a union of G and R, then if your R has a smaller amplitude, let's say if your K, let's say G is K regular and K is assumed to be larger, much larger than log n or log n, which is the maximum degree of a graph with inverse linear probability, then the maximum degree stays basically the same, k plus little of k. Okay, and therefore that's the best you can get. So that's as far as this k in the result goes. Now, how about square root n? Square root n up to this log factor here is also optimal because of the following consideration. It's known due to the result of Erdos and Feitlovich that for a random graph GNP with constant h probability, typically you don't get a very large topological minor. You get topological minor only of order square root n. And therefore, if you go to the very extreme, if you take your G to be a random graph G n 1/3, if you take your R to be a random graph G n 1/6, namely you are willing to add even quadratically many random edges, still once you take a union, what you get here is a random graph with probability which is somewhat larger than 1/2, but still away from 1, and therefore typically a complete topological minor will be of order only square root n. So we don't recover in the result this square root n here entirely. We have it up to this logarithmic factor. That's another place for possible improvement. Here somehow our techniques has this log n factor inherent here, but perhaps the result can be. So that's about the results. If you have any questions, that's a good time to ask, because I'm going to describe you some ideas from the proofs. So apparently there are no questions, so let me give you some ideas for the proofs, and I will discuss ideas for two theorems. The first one is theorem 2. So to remind you, you have a graph. Theorem 2 is about the diameter. You have a graph on n vertices with minimal degree k. We impose a random noise G and P, and P is taken to be much larger than log n over k divided by nk. We define Q to be 1 minus 1 of minus P, all this to power k squared, which is roughly P k squared. And then with high probability, what we get for the diameter of G union R is an expression of the order log of n over k divided by log nq over 2k. So here's a proof sketch. And the proof sketch follows a very typical pattern here. So because you assume some things about your graph, you can get some nice structure supporting your proof. You cannot quite take it all the way there to diameter, whatever your property is, because otherwise you don't need random noise. But because of your assumption on the graph, typically what you have there is some nice property or properties which take you almost there, and then you need to add this little random twist to take it from almost there to there. So here's our preparation stage. So the claim is as follows. It's a deterministic claim, fairly easy actually, and I will indicate you how to prove it. So we have a graph of minimal degree k. Then you can partition its vertex set into pieces so that the pieces are as follows. Each of them is of cardinality at least k plus 1, and the radius of each piece is at most 2. Namely, in each piece there is a vertex which is a distance at most 2 from any other vertex in the piece. So in particular, this means that the diameter of every piece is at most 4. And the proof is actually fairly easy. What you do is you take a family script S here, of maximal by inclusion family of disjoint stars with at least k leaves. Okay, so you have such a family because of your definition. So S is at least one due to our assumption. So let me denote by Vi the vertex set of each star, and let me denote by Vi the corresponding center of the star Hi. And our situation is like this. You take the stars array, and what you now have now is a graph H. Now, in this graph H, since you have stopped, you don't have any vertex in this induced graph H. You don't have any vertex of degree k. All degrees went down, which means for every vertex inside H, it has lost one of its neighbors in the stars, which means every vertex within H has a neighbor in the union of the stars. That's very good, because what you can do now, you take it there. If a vertex is connected to more than one star, just attach it to arbitrary star of your choice. So perhaps more than one choice, but you can attach it somewhere. So here's the picture. You have your stars here. You have your H. You take a vertex here. You know that its degree is no longer full. It's no longer k. And so it sends at least one H to one of the stars. It sends it, let's say, to HI. And then you can take V to HI. And the distance from V to VI will be at most 2. And you disbundle your H completely. Okay. So altogether, after all this operation, which is fairly simple, you get a partition of your graph into pieces, the same number of pieces as before, but now you have a full partition. And since each piece Ui contains inside Vi, we know that the size of each Ui is at least k plus 1, and all vertices in Vi are at distance at most 2 from Vi, which means what we get in every piece is a graph of diameter of radius 2 and hence diameter 4. That's a very easy decomposition. Okay, now for technical reasons, not strictly necessary, but it makes the proof somewhat simpler. You take your pieces and you chop them into parts which are more or less of the same size. Each piece is of cardinality at least k plus 1, but some of them might be much larger than others. So it's convenient in the proof to chop the pieces into sub-pieces Aj of cardinality anywhere between k and 2k. Of course, you can do it. And what you inherit is that for every pair of vertices in Aj, they are a distance 4 in G. So since you chopped it into pieces, it could be the case that you are not able to go from U to V inside Aj. You don't care. In the ambient graph containing them, you still can go from U to V in at most 4 steps. That's okay. And now comes the probabilistic part. Okay, you put random noise R on top of your graph, and you define an auxiliary random graph, which I denote by R star. So R star is defined as follows: its vertices are the pieces Aj, and you put an edge between a piece Ai and the piece Aj if and only if the real random graph has an edge between Ai and Aj. So what I get here is a random graph. It's a really random graph. The edges are independent there. Edges might appear with somewhat different probabilities. So Qij is probability of an edge between Ai and Aj. And since the pieces are of size at least k each, Qij for any pair Ij is at least as large as this value of Q we defined before, which is 1 minus 1 minus p to the power k squared. Okay. So you get a real random graph R star, and the point is that from a small distance of a small diameter of R star, you can go very easily to a small diameter in G union R. Here's an illustration why. So suppose in R star you can go from Ai to Aj to Ak in 2 steps. Then I claim that you can go from in the real graph from Ai to Aj to Ak in a constant number of steps, because you from any vertex to any vertex, actually you hop from any vertex in Ai to a vertex connected to Aj in at most 4 steps, perhaps going outside of Ai, but you don't care. Then you jump from Ai to Aj. Then you go from the entrance point to Aj to the exit point in Aj in at most 4 steps. Then you jump to Ak. You go to at most 4 steps in any point from Ak, and therefore altogether get that the distance between any point in Ai and any point in Aj is what's given on this picture, which is 14, I think, here. Okay. And that's nice because R star is a real random graph, and its stochastically dominates random graph is the same H probability Q, and therefore you can take off the shelf known results about likely diameter of random graphs. And the in particular result we are using is the following one. So with high probability, the diameter of R star is at most 1 plus level of 1 log of n over k divided by log n q over k. You need to recall here that we assume P to be much larger than log n over kn, and therefore in this graph R star all degrees are more or less the same, and we can apply this result about diameter. Okay. And hence, using this connection between the diameter of R star and the diameter of G union R, we get here that with high probability, the diameter of G union R has the same asymptotic order as the estimated. So that's the proof. As you can see, this proof, you can easily recover the missing details. This proof is not so complicated. That's one of the reasons I choose to present it to you here. Okay. Let me now present you a somewhat more involved proof, theorem 4. Theorem 4 is about topological cliques, and it goes like this. So here's a reminder. We start with a graph on n vertices. We assume its minimum degree is at least as large as k. We assume k to be tending to infinity with n in arbitrary pace. On top of this graph, we impose a random noise, and we impose a random noise of intensity C over n. C is sufficiently large constant. Okay, we will see when the proof we need it. Okay, then with high probability in the union of G and R, there is a fairly large topological minor. How large is fairly large? Is afforded at least minimum of k and square root of n divided by log n. Okay, so here's the proof sketch. You start again with preparing G. So, and the lemma goes like this. It's again deterministic lemma, which will be applied to our graph. So suppose we have two integer parameters, both are positive integers, and s is much smaller than n. S squared is the most n, but s is at least 8. Okay. So you take a graph on n vertices, and this graph is assumed to have minimal degree s. And what you can find fairly easily actually is a collection of stars of cardinality linear. And you can find linearly many in S stars, which are disjoint, and each of them has linear many in S leaves. Okay, so that's a lemma. It's not hard to prove. You can think about it as an exercise. Exercising is good for your body and for your soul, so you can try to prove it yourself. That's a fairly easy, and S over 8 and S over 4 are not necessarily optimal, but the idea would be to show linear many stars in S of linear size each. Okay. Very good. And now comes the probabilistic lemma. And probabilistic lemma goes like this. So we start with G and C of n, and C is assumed to be sufficiently large constant. And with high probability, the following holds. You take a fairly large subset inside the graph of subset of cardinality 0.9n. Now, in this case, the H probability is C over n, which is large, but not that large. So, for example, you have a fair amount of isolated vertices, etc., etc. So, in particular, in your set U, you might have some isolated vertices. So, you need to clean it up. But the point is that inside U, there will be a set U prime of cardinality, which is roughly comparable to U, 0.8n. Okay, so that this piece has diameter logarithmic n. This dependence on C. The beta C is the smallest the diameter of the diameter of the logarithm. That's a very standard statement which appears in many, many papers in random graphs. I'm looking at Benny. I'm pretty sure that Benny has it in something like 5 papers at least, including probably a couple of papers with me. So that's really easy to prove. Here's a very rough sketch. It's standard, very standard argument. We first argue that inside U, you can find U prime, of the right size and of a large minimal degree. Just start deleting vertices of small degree one after another, and after a while you run out of steam and you stop with many, many vertices, and minimal degree will be large by definition. And then you argue that in your graph, in your random graph G and C of n, typically every graph is a large minimal degree, is an expander, and as such it will have a logarithmic diameter. So that's a very, very standard argument for the graphs. You can think about this as an exercise, okay? Or try to read one of Benny's papers or my papers for this. That's really fairly standard. Okay. Okay, now let's proceed to our business. So we need to get a large complete topological minor. So let's set the goal explicitly. The parameter L is taken to be the minimum of the minimal degree delta of G divided by 8, and some small constant, small enough constant C, n divided square root of n divided by log n. Okay, and the goal is to find topological minor of KL in G union R. That's exactly what we need. Okay. So by lemma 1, we know that there are stars S1 up to SL, and each of the stars has cardinality or has number of leaves linear in L. That's good enough for us because these stars will serve as a basis for our topological minor. That's a very, very standard argument about getting large complete topological minors. You need to start with the centers, and these centers have disjoint stars next to them, and out of these disjoint stars, you will use the disjoint stars to connect between the centers. Okay, so let me note the leaves of the stars by x1 up to xl. So the cardinality of each xi is exactly 2l. Okay, so here's the picture. There are centers s1 up to sl. There are leaves x1 up to xl, and each of the set of leaves has cardinality 2l. And besides it, there is a set u. So u will go and shrink, but still u will be at any stage of the proof of cardinality 0.9n, and therefore this probabilistic lemma I stated before will be applicable to this u. Okay? And the idea would be to construct a complete topological minor of size L with S1 up to SL being its branch vertices. Okay? So how do we do it? So you do the following thing. You go over each pair ij for I less than j between 1 and L, and you take the next available vertex x prime in xi. Now and then you will lose some vertices, but you will proceed with persistent, and you try to connect it to next available vertex x2 prime in xj through u prime. Okay, so the picture will be like this. You take the next available vertex here in xi, that's x prime. You take the next available vertex x2 prime in xj. You go to a set u. Your set u perhaps has not much structure, but inside it there is a set u prime of diameter logarithmic n, and therefore, if you are able to jump using your random edges from x prime to u prime and from x2 prime to u prime, then by the property of u prime, you are able to connect these 2 points by a path pij of logarithmic length, and therefore altogether you get a path of logarithmic length between x prime and x2 prime. You take this path, you delete it from u, you delete x prime, you delete x2 prime, and you proceed. Okay? And since you need to repeat this operation at most constant times n over log 10 times, because of this square root of constant n over log n in our statement, after all this deletion, you still have set u of cardinality 0.9. So let's see why it succeeds with high probability. So as I said, we find at any point of the proof, we are left with a set of u of cardinality at least 0.9n, and therefore we are able to find a set u prime of logarithmic diameter. And now at this point of time, you expose your random edges from x prime and x2 prime to u prime. So use this gradual exposure, you expose random edges only when you need them. Okay? If you are lucky enough, you will have x prime connected to u prime, you will have x2 prime connected to u2 prime. Now, what's the probability of not having such an edge? You have a set u prime of cardinality 0.8n. H probability is constant over n for a large enough constant, but not that large actually. And therefore, the probability that you don't have such H is a small constant, much smaller than 1/2. And therefore, if x prime and x2 prime are both connected to u prime, then you connect them by path pij, you delete x prime, you delete x2 prime, you delete pij, and you proceed. You still have lots and lots of vertices to construct u and to construct your set u prime in the next steps. Okay. Observe that the argument about u prime is deterministic. Okay, it follows globally from the global properties of GMP, and you don't expose your randomness again and again there. Okay, so if you fail on x prime and x2 prime, then you delete the vertex you fail at, and you hope that with the next vertex in the same bunch xi and xj station will be better. You move to next available vertex. So let's see what's the probability of you to fail. If by the end of the day you fail to do it, this means that for some particular I between 1 and L, you fail at least L times. Xi has cardinality to L, and you didn't manage to connect Si through Xi to all the guys, which means you made exactly 2 L attempts, and you failed in at least L of them. The probability of failure at every attempt is a small constant. These probabilities of failure are independent for different trials, and therefore the probability that you fail for this particular set xi so many times is exponentially small in L, and the number of pieces is only linear in L, and then by applying the standard union bound, you see that the product of L and the negative exponent of L is literal of 1 if k tends to infinity, and therefore by the union bound you succeed by the end of the day to connect every Si to every Sj, and what you get here is a minor, a topological minor of KL with branch vertices S1 up to S3. Very good. That's what I wanted to say, and thank you very much for your attention.
Yes, thank you very much, Michael. So thank you very much for this beautiful talk, Michael. So now the time to ask questions. So you can unmute yourself. If you have a question, just please directly go ahead and ask. So maybe I will begin. So this is kind of a very nice model for graphs. You can apply it also for hypergraphs naturally, although I know much less such results, right? People still didn't do that.
Sure. Well, yeah, as you surely remember, for example, you can apply it to hypergraphs, and with you and with Matthew have hypergraphs. You can apply it to directed graphs. We also have a paper we can apply it to even to Boolean functions. We have a paper with prosaic. I think the beauty of this model is kind of extremely universal in the sense it's just not exactly a concrete model, but a general approach. You have your instance, your combinatorial instance, which is a Boolean formula, a graph, a directed graph, a hypergraph, maybe even a matrix, and you are not yet there. You have some structure, but this structure is not enough by itself to bring you to your target property, and therefore you can hope that by perturbing it a bit, usually by adding some random noise on top of it, you can get what you want to get.
Yeah. Yeah, so indeed Boolean function is good to mention. Right there you wanted to make a Boolean function not satisfiable by adding only few random clause, right?
Exactly, correct. You can assume that you have a satisfiable Boolean function, and as you can imagine, if this function, Boolean function, is let's say it's a KCNF formula, so it might be satisfiable, of course, but if it has many clauses and it's kind of shaky in the sense that you're satisfiable, but in a rather limited number of ways, and therefore you can hope indeed that imposing some random noise, adding some more random clauses on top of it, you'll be able to destroy satisfiability with high probability. And that's indeed our result stated in formula with Benny and Prosaic from also something roughly 20 years ago.
Right, so I got a question. So if I remember correctly, for these 4 theorems you proved, if you assume the A1 assumption, then the optimality is always obtained by a bunch of cliques, or maybe in the last theorem, you can also take a random graph, right? So can you show that these are the only 2 extremal cases, basically? I mean, if suppose the parameter you consider is sufficiently nice.
Just a moment. Okay. You can make it more sophisticated. So basically, if I understand you right, what you are saying is even in addition to A1, you also assume some structure of your graph. This might make it easier, because if you assume A1, nothing prevents you from taking disjoint cliques. If in addition to A1, you assume is some kind of connectivity results, focus on some concrete result maybe here. So here they say the optimality is fairly prosaic, you take cliques, but if in addition to assuming a minimum degree at least k, you assume something maybe about connectivity, or maybe about some structure or some age distribution, you can make it better. Okay. Since all of us are apparently in constant search for problems, let me maybe mention some examples kind of in the vein of your question. So there is a fairly well-known, I'm not necessarily being very modest here, fairly well-known conjecture of Benny and myself about embedding things in n-lambda graphs. You take a pseudo-random graph and you want to embed there. So in our conjecture, you want to embed a Hamilton cycle. Okay. So, and you would like to get a starter from the spectral ratio being just large enough constant. That's not known, so we need to do it for something like log n. Now Ben and his students have some improvement up to cubic root of log n, correct, Benny?
Yes.
Okay, so you can instead ask the following question. You take your n-lambda graph and you pose a little random noise on top of it. What can you get? And actually, it's quite easy to see that by imposing little random noise, you can get your Hamilton cycle fairly easy. A more challenging question, apparently a much more challenging question, is you want to embed a tree. You have your bounded degree tree on n vertices. You want to embed it into an n-lambda graph. That's probably quite hard. It might be true if the spectral ratio is large enough, but that's hard. But maybe an intermediate step to go forward is to take n-lambda graph to impose a little random noise on top of it and to get your tree. Which means you assume some fairly rigid structure, which is not enough. It's not known to be enough to take it all the way there, but then you can hope that maybe you can, by this little random noise, go all the way to your target. I hope I answered the question.
Yeah, I see. Thanks, Michael.
Sure.
So Michael, I have a question. So since you mentioned the generalization to digraphs, so suppose we want to find the Hamiltonian cycle in digraph, what kind of like a natural condition we impose? Do we say something about like a semi-degree or something?
I guess so. Semi-degree would be kind of a natural assumption to make, correct? Because you cannot assume a large in degree only or large out degree only. So semi-degree would certainly be natural, but maybe even. So, Benny, do you happen to remember any results from this? There might be some results.
If you only assume out degree or in degree and you had very few edges, you might have linearly many vertices with out degree 0, right? Let's say complete bipartite directed graph that way. And then
correct.
You will not fix them, right? By few random edges, you will not add them in degree even 1, and therefore obviously will not have Hamilton cycle. So somehow assuming both in degree and out degree seems at least necessary.
Or at least maybe maybe the assumptions don't have to be identical. So maybe if you assume large in degree and somewhat large out degree, you can get something. But so this was strong, but I am not sure I remember all the literature. There might be some results about it, so it was checking first. That's in the vein of this result. Yeah.
Actually, the three of us have a paper where we prove that a pancyclicity condition after randomly adding some edges.
So by the voice, I recognize Matthew, correct?
That's right. Yes. Sorry.
Okay.
So, yes.
Nice to hear.
Yeah.
Okay.
But again, it's right, like Michael said, it's pretty open. I think the results are becoming interesting depending on like, because it's like a two-stage thing. So one, you're showing how to use randomness, but also before even you do randomness, you do pre-processing. And many times, right, you can prove interesting structural result about graph which have certain properties, some simple but nice structural result which you also need. So if you find an interesting class of kind of directed graphs which by themselves they have nice structure but not enough for Hamiltonicity of other things, then you're getting a result that with a little bit of randomness you can fix it.
Yeah, so maybe let me mention one more thing. So for example, if you look at this result of Bowman, Fries, and Martin, so they assume a very large minimum degree and fairly mild assumption on independence number in principle, and that's what we did in the previous paper with Elad and Dani. Instead of assuming linear minimum degree, you can assume your minimum degree is n to the power 4/5, for example, some much smaller function of n, and then you can start playing with the parameters. Say, okay, if the minimum is such and such, and your alpha is such and such, which amount of random is doing it? So in a way, it's a really fairly large spectrum of questions, and you can play with it. You don't have to assume that all degrees are linear. And you can impose much weaker assumption on the degree. You will pay for it in the amount of randomness and then your assumption about alpha, but there's still really a lot of room to play.
So now I become very curious. So in your dialectic graph, let's say the minimum out degree is at least n/3. So can you say that if you randomly perturb this a little bit, they always contain a dialectic triangle with high probability?
Say it again. How somehow I don't hear you.
So
very clearly.
basically your version of the Cassetta-Hargreaves conjecture for triangles.
But with the help of randomness, right? You start with a minimal out degree n/3. So we believe that the recti triangle is already there, right? But we don't know.
Yeah. Okay.
Right.
But now you add a little bit of
I don't think it's known. It's a very legitimate question. So
but wait a minute. But if can I ask something? So if you have a minimal out degree n/3, right? By averaging, there would be some vertex whose in degree is also big, right? Right?
Yes.
Right. Just so therefore you will have vertex with big out degree, big in degree. You can make this even these two sets of linear size. So it means just one directed edge in a correct direction there will fix it. So it means that you know 1 over constant over n square is probably will work, and maybe so maybe here it's actually right 1 over n square will do, right? Simply because for some particular vertex.
Yeah, but in general, what's so it might sound like a poor man's version of extremal graph-theoretic result, but there are lots and lots of nice conjectures, and they are apparently very hard. And I think it's an intermediate step in establishing these conjectures. So a typical conjecture in extremal graph theory goes like this: you assume property A of graph G, and you'd like to derive property B, which might be hard. Or might be even not true if that's not a conjecture, it's a false statement, but you can say, okay, you take your property A. Unfortunately, we are unable to prove that it implies property B, so let's add some randomness and let's try to prove property B. And this actually might be even helpful in establishing the real conjecture, besides being interesting on its own.
Perfect. So maybe, right, so not to go too much over time if people need to leave, maybe let's stop here. Let's stop recording, right?